Okay, so next we have Miljan Vuletic from Switzerland, who is head of engineering in Darwin Digital. Miljan is a computer industry expert with broad expertise in software development. He also holds a Doctor of Philosophy focused in computer science and architecture from Ecole Polytechnique, Fédérale. Sorry if I'm not saying it right,
Never mind.
Lausanne. Okay. Yeah, and he will talk about Edge AI framework for healthcare applications. The mic is yours. Thank you.
Thanks, Philip. Thanks, everyone, for coming to this presentation. First of all, I would just like to say that I'm a bit not used to this kind of virtual event, so I've been cheating. I have real colleagues sitting in front of me, so if everything goes well, it's their fault, and they are going to provide their facial expressions and feedback to stop me disseminating some stupid things. So hopefully it's going to help a lot. So thanks for coming. I'm going to present you our work on the Edge AI computing, and maybe just give you a little of the background about Darwin. Darwin is a company based in Switzerland, Lausanne, EPFL, the Swiss Federal Technical Institute, and we also have our offices in Belgrade and in India. And we specialize in providing services and solutions in the field of Edge AI, especially in the industries of automotive, healthcare, and manufacturing. So in this presentation, I'm going to present a kind of light technical talk that is accessible to most and broad public. And my goals in this talk would be to explain that what is Edge AI, why is this important in medical field, what are the challenges, to give an example how we solve these challenges, and maybe provide some use cases. So this task is going to be easier because we have seen in the previous talks that my previous speakers have explained very interesting use cases and very interesting techniques. So we are working in the similar field, and we are specializing in edge and IoT solutions for artificial intelligence. So to continue with the talk, I'm going to explain what Edge AI is. It is basically using, instead of using artificial intelligence and running inference models on cloud and large computing platforms, we are using specialized platforms that are optimized for low power and still can provide acceptable performance for the applications. These platforms have some hardware accelerators for deep learning. They support heterogeneous computing because they have different computing resources like accelerators, GPUs, and customized hardware execution units. We are capable to see, and we can see on the market, there are different providers of this kind of solutions, like semiconductor industries and companies like NVIDIA, NXP, Synaptics, ARM, Intel extensions for vectorized processing, etc. We can see that these suppliers of silicon devices target various applications in set-top boxes, smart sensoring, non-intrusive monitoring, smart shops, etc. But one of the hot topics, as we have seen in the previous talks, is the application of artificial intelligence and edge technology in the medical and healthcare system. What we gain from these kind of devices when using them in the field is having acceptable and targeted performance, well-tailored performance for the application, with acceptable power and size advantages that are much better in comparison to large computing centers and the cloud. What are the benefits of the Edge AI, of running the AI applications on the edge on small embedded devices? Well, first thing to notice is that it can be an offline execution. Now we are all over-connected, and we are taking advantage of the internet everywhere we are, but there are some situations where we must not rely on the network connectivity to be able to monitor and signal or notice some irregular behavior with the patients, for example. So we are not requiring the network connectivity and the large bandwidth. We can rely on autonomous devices that are sometimes battery powered. And this is something which enlarges our deployment scale. So our devices, in that case, if they are not reliable on network connectivity, can be spread and deployed everywhere. To give you an example and to illustrate this kind of connectivity that can be low bandwidth, take an example of LoRa, which is long-range wide area network that is being used more and more in the embedded world and IoT world. And then there are also other techniques and standards like Bluetooth, low energy, etc. So this is a kind of communication infrastructure that allows embedded devices and very low power devices to communicate and send their data, but from time to time, not in a permanent way. Apart from that, what is guaranteed when you don't need the network and the cloud for computation is that you have that you can achieve low latency. You can take decisions and make real-time systems much easier to construct and design. Because you are avoiding lengthy communication cycles, real-time decisions are available at the very devices and the very computational nodes. And last, and not the least, these kind of devices can address an emerging problem that we see now in Europe and all over the world, and it is about the privacy. So these devices not necessarily need to send images and videos across the network, and they can do their analysis only the data that is really concluded out of these images and networks is sent over the network. So in this way, we are addressing privacy in the best way we can. And then why edge AI in medical? I think these examples also respond to this question, because combining these features, we can achieve and build devices that are easily and reliably deployable in the medical healthcare systems. When it comes about the challenges, what are the challenges that we need to address when we design healthcare embedded AI systems? Well, if we want to deploy state-of-the-art models on devices with limited resources, as sometimes these devices really are, we have to answer several questions. How to adapt these models that really work well on highly computing resources and available computing engines on the cloud, but how to adapt them and squeeze the models, make them deployable on very low power and limited computational resources devices. So this is something that is critical, because we must not deteriorate the performance of such devices when it comes to the medical applications. We also need to reduce the model size, but also the number of parameters. We potentially can use fixed point instead of floating point computations, and tune the models and their architectures to the in-field data. When I say in-field, I mean we usually have general models that we can take off the shelf and then try to apply them in the real applications. But what we realize is with the lack of real data in the field, in-field data, it is very difficult to have these models perform and reach the key performance points, KPRs, right? So in order to do that, we usually are exposed to collecting data in the field, which means that we need to tune our models to the real data. So there is a whole machinery that is needed and required to collect the data, annotate this data, and reuse that data in order to improve the existing state-of-the-art models. So then this is really a big challenge. So we are talking about data challenge, because in these applications we must ensure that we reach really stringent performance goals. Then another thing that is a challenge in this kind of applications is that we need to provide optimal mapping to heterogeneous computing resources, because we have different resources, as I mentioned, GPUs, accelerators, CPUs that run in parallel, and we need to optimize their use in order to guarantee that we minimize the power and we optimize the performance. Apart from that, we also may interfere with context switching, because these applications, these boards can be used with some different, the application may be shared with some different other applications. And we also must not forget there is always a security threat that these Devices can be tampered and abused, so we need to provide really a trusted and secure execution environment. To give some more details about, for example, promising techniques that can guarantee squeezing the model size and optimizing their size and the number of parameters for the execution on the embedded platforms, we can apply techniques like pruning and quantization, but again, these kind of techniques may require again, retraining the models, readapting the models, changing their architecture. So this is a burdensome task, and in Darwin, we try to develop tools that help us in this task and facilitate our design cycles. So when we talk about the optimal mapping to heterogeneous computing resources, we have different suppliers of hardware that use different techniques. So on one side, we have SIMD, which is single instruction, multiple data way of executing computer programs. Then some CPU suppliers, they provide their own instruction set extensions like ARM-NN, neural networking, or ARM-SVE, scalable vector extensions. These kind of extensions support optimized execution of matrix operations, linear algebra operations, and we all know that these kind of operations are very widely spread in the inference of artificial intelligence algorithms. And then we have accelerators like provided by NVIDIA in the form of GPUs or other platforms like NXP that they have their own network processing units. So in order to map in a general way your applications to different and really heterogeneous hardware platforms, you need to have some support and good tools that allow you also to shorten the design cycles, not to spend too much time in designing the things or moving from one platform to another. Why is it important? Because if you figure out that you cannot meet the performance and power budgets on one platform, you decide to move to another platform, you want to avoid the whole development cycle that is related to mapping and optimization of the computational resources. A good example of such environment and such framework is a Bonsai's project and the result of this project. So this is a EU Horizon 2020 project that Darwin has participated in building. And it is basically a platform for exchange of AI-related artifacts and also a set of development and design tools for developing AI applications and for deploying them on different supported platforms. So you can see that beneath this structure and the agents that interact, there is some common layer, which is Bonsai's marketplace. And there are some also Bonsapps, which are Bonsai's tools that and the flows that support AI deployment and development. On the AI marketplace side, the innovators, so people who come with ideas, who come with challenges, they define challenges and send these challenges to data scientists who create AI assets. AI assets is basically a way of solving the challenge. So it is a high-level AI model built using some standard development tools like PyTorch, Keras, or whatsoever, with some standardized interfacing and interchange of the AI artifacts. So in this way, innovators and data scientists can exchange their information through the marketplace and iterate in order to solve the problem in the best way. When the problem is solved, we have created an AI asset that is now ready to become an AI application. An AI application is an optimized model ready to be run and deployed on different embedded AI platforms in a very, very easy and convenient way, thanks to the Bonsapps support. So once we have the AI apps, the developers are ready to benchmark, test, and see whether they perform as they are expected to. And as a final step, we have the integrators who take the AI apps. So these are well-defined standalone modules that can be combined into AI solutions. And AI solutions basically combine different AI models and algorithms in order to solve particular problems. So be it in healthcare, be it in automotive, be it in manufacturing or other field of applications. So basically these are kind of customized flows containing some building blocks that are proven to work well on the target platform. And if we, for example, decide to move from one platform to another platform, the Bonsai's framework supports us and allows us to do it really seamlessly. Being motivated with this Bonsai's work, we have also provided a tool that we called MATE and Framework. This is a model audit toward endorsement tool. And this tool allows us to tailor AI models to the embedded AI platforms in a very standardized and flow-oriented way. So we have a way of wrapping the input coming from the research, coming from the state of the art, and the leading developers of AI in the world. And it allows model integration, optimization, and deployment, tuning, and adaptation. So endorsed models can be efficiently run on different target platforms because of the tooling support, and it provides us a standardized flow and a set of standardized interfaces and wrappers to guarantee that at the end we reach our performance and power goals. So the major blocks are normalized model part, then we have the evaluation part, which relies on the evaluation data in order to evaluate the performance, evaluate the precision, evaluate other parameters that are defined by the developer's side. And there is, of course, a feedback based on these results, evaluation results. We can go back and retune the models, retrain the models, and also optimize its architecture, data size, and the number of nodes and the parameters. Once we see that the model is well performing and reaches our performance goals, we can do the inference on the target platforms and then measure real performance and do the mapping to heterogeneous computing resources. We have also the cross-validation part, which is basically related to execution of the models on target platforms, but not only target platforms, also on target inference engines. We can see that when you need to transform a model from one inference engine to another inference engine, the format and the operators may need to change, and then you need somehow to guarantee that the model behaves in the same way it was in the original model. So you need some firm tooling and tailoring of the models in order to achieve that goal. So one other thing to mention also is that it is sometimes required to map to different layers, and during this process we can discover that some layers are missing for given platforms. So in this case you have to provide some plugins to emulate the layers. When I talk about layers, I think about neural network layers and their implementations. So within the framework, once you deploy and you want to deploy on a given platform, you can see that some layers are missing and some are not implemented, which is a common thing that ML engineers experience in their everyday life. In order to solve such problems, to identify such problems, our MATE framework can isolate these things, and also we can easily provide the implementation for the layers, and then reiterate again, show that the layers are performing correctly, and complete the development for a given platform. So this is a very important part of the embedded AI development. Now, having given this technical background and how we address these challenges of the embedded AI edge AI development, I'm going to show you context in the healthcare and the medical field that we can easily address and solve some real-world problems. So to give you a context, this is a simple use case in healthcare that I'm going to present to you, and we have seen also that this kind of cases also motivate other people in the previous talks. So this is something that is really interesting, and these applications are going to see the daylight in the following years, I guess. So we can help the elderly population in the world. We can help with the COVID-19 isolation, and also we can help depressed people who are isolated because of the COVID pandemia. So we can follow and watch human behavior, of course, locally at the edge without sending these videos and images to the cloud, and we can follow their state. This is a very simple case where the state of a person can change from standing, walking, to falling or lying on the floor. To be honest, we are also investigating more complex cases that also require knowledge of the human movements and human behavior, and these are related to neurological diseases like epilepsy, autism, or similar. But here I'm not a physician, so I'm not going to go into more detail about these projects and use cases. Here is a very simple one that is understandable to everyone. What is the challenge here? So in the current approach, we have either manual, surveillance of patient and personal care provided by healthcare professionals. And we have seen, and it was mentioned in the talks before, that this kind of personnel requires at the end a lot of resources and raises the cost of the whole medical care system. There are also automated approaches, but they are mostly cloud-based monitoring or imply some variables, as we have seen, that can be used to monitor some vital parameters of the elderly people or patients. So there are different burdens in these existing approaches, like there is a financial burden, there is also privacy intrusion with all of these GDPR rules and consent required for everything. So we have been storing data on the network that belongs to patients. And of course, we are experiencing more and more, especially in the Western world, the shortage of trained healthcare professionals. And the solution that logically comes to one's mind is, let's provide patient monitoring at the edge. And here is our example pilot project called Kestrel, which is a privacy-preserving app to autonomously monitor patients and elderly residents in hospitals and care centers. So this little box can, by analyzing signals coming from its sensors, detect the state of the persons in the room where the device is deployed. And what is behind the curtain? So what is the technology being used? So there is, in this case, it can be any embedded board with sufficient power computational resources. In this case, we have chosen an NVIDIA board, Jetson Xavier NX, which has a decent computational power, but still it is really small. It has a small size factor, and also it is easily deployable and embeddable in devices to be deployed in the field. And this really represents a very good example of computer vision at the edge, where we combine the heterogeneous computing resources of NVIDIA embedded platforms with the application to help the patients. Now, how it works in practice, unfortunately, I haven't got any videos to share with you, but and also I haven't got elderly people falling or standing around. It was difficult to find them. But we have explored the possibilities of the device with our younger colleagues who were acting as models, and we were able in real time to analyze their state and also alarm the changes of the state that may be of interest for healthcare personnel. So we are having the first layer here that is based on some state-of-the-art body pose detection models. And as an output, these kind of models provide a timeline stream of points that are changing over the time. As a second layer, we are proposing a custom layer processing these time signals, and using either classical or machine learning methods. We use this signal series in order to detect state and the state change, and then alarm and send it to the person in charge. So we were able to efficiently apply these algorithms in real time on embedded platforms. As a conclusion, well, medical or healthcare applications can really leverage from the embedded AI and low latency, because there is low latency and enough processing power. We can do it in real time, and we can answer some concerns related to the privacy and the cost of deployment. In our solution, we are using a robust development framework, which shows to be a necessary tool in order to find optimal solutions that can run on different platforms. And this tool provides us seamless porting of the state-of-the-art ML models across different heterogeneous computing platforms. We have developed tools to prototype, port, and validate AI models in a hardware-agnostic fashion. Means that you need not to think about the target hardware platform. You can concentrate on developing the algorithm, and the tooling and the platform support will automatically provide and guarantee that it will run. Of course, with a lot of work behind by the ML engineers, but at the end, such tools are feasible and achievable. So we have shown the utility of the framework in a real-life body pose estimation application. And it works quite well in real time, and it can be tuned to really be able to alarm healthcare personnel in the case of accidents. What we have planned for the future related to this application, well, we need to improve the tools and provide automated constraint optimizations to target even smaller and even more power stringent and computational performance stringent devices. And we also want to explore and continue extending our expertise and doing the expertise transfer from medical experts. So working together with medical people and trying to detect behavior, human behavior related to some neurological diseases. This will conclude my talk, and I thank you for your attention, and I will be ready to answer some questions if there are any.
Thank you, Miljan, for inspiring and great presentation. We have 45 seconds left, so if anyone has the question.
It was too just, I'm sorry.
Yeah, no questions so far. I guess that people can reach out to you directly on LinkedIn.
Yes.
If anyone has like any particular interests.
Please feel
thank
free.
you.
Thanks, Philip.
Thank you very much, and we'll have 15 minutes coffee, toilets, and other breaks. So yeah, we'll come back to the program in 15 minutes. Stay with us.